Cool. Okay. So why exactly do we assess CryoEM structures? Well, CryoEM structures are becoming a really common experimental method, and we're able to obtain really, really large structures from them. It does have a problem though, and that is that the data itself is really difficult to interpret. It's very variable, it's very noisy, and the resolution fluctuates really wildly, especially compared to, say, crystallographic data. And traditionally, CryoEM has really benefited from structure prediction because CryoEM has typically provided only low resolution maps. And so we've been able to take homology models and structure predictions and dock these into maps and from there get a picture of the molecules. And the CryoEM assessment is kind of unique. Predictors get given sequences just like usual, but the assessors have CryoEM maps as well as a target provided by the experimentalists. In CASP15 this year, there's 26 CryoEM targets. This is up 11% from last year. And a large number of these CryoEM targets are from RNA. We also have maps with multiple conformations. This is something that's kind of unique to CryoEM. When we do the image analysis, we can sometimes separate molecules in different states. And this is another really exciting aspect of the technology. And also since CASP14, deep learning is kind of encroaching, and we've got tools like Deep Enhancer, which is a sort of way of artificially sharpening CryoEM maps. And these will be really exciting to assess. In CASP14, we of course had AlphaFold 2 predictions, and these were really, really accurate, at least at the domain level. But of course, when you had multiple domains, the actual orientation of these were often off. And CryoEM was a really nice source of low resolution information, which could be used to reorientate these domains into the maps. And Tristan Cragnolini, who used to be in the group, did a lot of the assessment last year and developed some really cool Gaussian mixture models for deriving ensembles to better assess structures in low resolution maps. So using these Gaussian mixture models, you could actually produce a small set of structures which actually better reflect the data. And of course, since CASP14, the resolution that we're seeing in CryoEM maps is continuing to increase. And I think this year, the majority of maps are better than 4 angstroms. And this is really exciting because it means that sidechains are really visible now. And it's opening up new territories for structure prediction, because we can actually take the predictions, the CryoEM maps, and look at this high resolution information. Are the structure predictions matching CryoEM data at the sidechain level? Okay, so how do we score sidechains? The way we do it is for a given residue, we basically create a fragment and we fit that fragment to the CryoEM map. And the reason we create a fragment is because the structures always tend to be a little bit off. So we want to make sure the backbone's nicely positioned into the density. Once we've done that, we can then look at the voxels around the sidechains and assess how they fit. And of course, what we get from predictions is actually not density data, it's coordinates, right? So we have to take those coordinates and turn them into an EM map. And the way we do that is for every atom, we basically compute a Gaussian, and that Gaussian is related to the resolution. And we add all these Gaussians together, we get this map. And now we can take any sort of part of the experimental map and any part of our simulated map and do some kind of comparison using a scoring function. This is typically cross-correlation. All right, so the first structure I wanted to look at was T1157S1D1. The majority of the map was better than 4 angstroms. It's quite a large model, it's 661 residues. And there are actually a number of regions which are poorly modeled in the target itself, unfortunately. And there are also 3 major low resolution regions in the map where we can't really resolve any structural information. And so you can see here these green bits that are sort of outside of the density, those are in low resolution regions. You can probably assume that the structures are quite disordered there and flexible, which is why the EM map is so low resolution. When we look at our sidechain assessment score against the GDT-TS score, it seems to improve with GDT. So that's quite nice. When we actually look at the target itself, these are the kind of modeling issues I'm talking about. So we can see there's all sorts of side chains out of the density, right? In 153, there's a blob where that aromatic ring should go, similar in 26 and similar in 49. And you can probably also see in the background in 49, there's also a loop which is well out of density. So this is why we have CryoEM experimental maps when we do these assessments, not just the target, because the targets do tend to be a little bit wild. So here's one of the best predictions, and we can see the best prediction actually fits the data much better. And if we look at the top 4, that's also true. And there are also some low resolution regions in this map where the target was incorrectly modeled. So we can see here the target goes off. I've actually cut these loops just to make it a little easier to see. And all of our predictions, or the top 4 at least, did a much better job of fitting into the density. And unfortunately, there was also issues in high resolution loops. So over here we can see there's a histidine sort of up the top there, that should be sort of more in the density. And there's also a aromatic ring down there, which should be modeled into density, but that loop actually goes way off there to the right. So this is unfortunate, but that's life, and that's why we assess against the CryoEM map rather than against the target, because obviously RMSD is not going to be very useful in this case. Unfortunately, some of our predictions, despite being really good with modeling side chains and some of the loops, they also went off. So we can't rely on the predictions entirely. We do have to look at the map. I then looked at T1169, and this is a really this is the big complex, right? And I looked at domains 2 and 3, and the reason I wanted to look at these is because there's interfaces there, and if the side chains aren't fitting into the density, then maybe that's going to end up with interfaces which are poorly modeled. But before we look at the models, let's look at the side chain versus GDT S score for this structure. And again, we see a similar trend. But if we look at it in comparison with the first structure, overall it's kind of lower, and I'm not exactly sure why. The resolution of the 2 maps are very similar. They're all both around 3.4. So it could have something to do with maybe the difficulty of the target, but I'm not sure yet. So we've got domains 2 and domains 3. When we look at the CryoEM map, we can see that there's an aromatic ring there and an arginine which interacts with it, sort of pi-cation interaction. When we look at the predictions, they all put the aromatic ring well outside of the density. Right, this is true for the top 4 again. And if we rotate this around and look from the other angle, what's kind of interesting here is, despite the fact that they're oriented wrong, they've maintained this interaction. So they've still got the pi-cation thing going on, except for the one that's circled. That's off doing something else. Okay, and the final sort of data I was planning on looking at was the RNA-Protein Interfaces, and the idea was to do some CryoEM assessment. Unfortunately, the CryoEM maps were very low resolution and very noisy, and I gave up on that idea. So instead of using the CryoEM data, we tried to predict or determine whether the interfaces were present in the predictions, and to also look at the topology. And if we look at the target, it looks something like this. And this is one of the decent models. And when you try and overlay them, it just doesn't make any sense. And as we heard this morning, RMSD is a really bad estimate here. So instead, what I looked at was topology. So basically, if we follow the path of the RNA as it goes around the proteins, we see it sort of forms a hairpin with the first protein. It then goes on and visits another protein and creates a hairpin. It then visits a third one, and then it wanders back to the second one, creates another hairpin, but this time on the other side, goes back to the third one, and then finally back to the first, and then kind of ends in some sort of helical terminus, which is kind of hidden behind the blue protein in this picture. So this is what we wanted our predictions to hopefully match up to. So first we needed to define our contacts. And so the way I did this was to just take the target structure and then take all the nucleic acids and amino acids which had at least an atom within 5 angstroms of one another. It's fairly crude. And then we defined the contact score in terms of the prediction, the contacts and the predictions which match the targets, and we scored them using the Matthew correlation coefficient. And we can see when we plot the distribution of contact scores that it's basically bimodal. We've got a whole bunch of predictions around 0, which is basically a random for MCC. And then we have this group which is clustered around 0.4. And the top one, according to this score anyway, is the Gahara lab, and they sort of hit 0.51, I think. And what we see is if we look at all the structures that are in the top of this this upper cluster, they almost get the structure right. So they go to the first one, the second one, the third one, back to the second one, and then instead of going to the third one and the first one, they go to the first one and then the third one. So a lot of groups ended up doing this, both human and servers. And if we look at some of the worst predictions, like from the Baker lab, they only predict, or they only get some of the contacts. Okay, so as we can see, it's hard to define a target model from CryoEM data, which is why we provide experimental data along with the model. Sidechains are often, well, they seem to scale with the GDTS, but we're not exactly sure what's going on. We haven't had a look at enough structures really. And the RNA assessment was actually fun after all. So, yeah. Thank you. Any questions?
Questions?
I have one, if there isn't another one. In terms of I thought it was really interesting when you're talking about density agreement. Is this an easy thing for people to do with their models during development, or is there a really easy way to make this standard? Because if it's not standard, we'll all just go back to the PDB coordinates for everything we're developing.
Yeah, I mean, it kind of is standard. There's a lot of tools out there that do assessment of model against CryoEM data. But as you can see, we were given a target that clearly hadn't been assessed. In the top lab, we've got a tool called Tempi, which is a Python library, and that provides you with a lot of the scores that I kind of showed. We've got one called a SMOC score. But packages like Phoenix also do this. So that, yeah, they're really widely available, but I think people tend not to use them for some reason.
Any more questions?